Okay, our next speaker is Michael Cashmore, and he will be talking about short-term human-robot interaction through conditional planning and execution.
Okay, this is actually, it's quite similar work to the previous talk, and it's a joint work that we did with Luca and Valerio Sanelli. I'd like to point out that this is short-term human-robot interaction through conditional planning and conditional execution, right? Not just human-robot interaction through execution, which, I mean, sounds obvious at best. That's cool. So we're interested in the domain of service robots, which is quite an interesting domain coming from the planning side, in that you're in a situation where you have very little information about what the current state looks like. Because you're dealing with humans and their actions in the state are going to be unpredictable and their needs are at the start not known, you only have a very small amount of the initial state in your model. And if you make any assumptions about the things that you don't know, you run the risk of, well, for the plan failing and replanning, which can make the robot look as though it's just not intelligent, or a worst case, frustrate the user. And this is something we want to avoid. So in particular, for this work, we were building a framework to run on service robots to combine conditional planning and conditional execution for really short-term interactions with non-expert, untrained users. This means users who don't understand what is planning, they don't understand how the system's supposed to work. And more than that, they've not been trained to use the system, so they don't even, they're not expecting what buttons might appear on the tablets. The interactions are shortened with new users each time, which means there was no need for learning between interactions. Each interaction was completely fresh and identical to the previous one at the start. Downside to that, though, is that each user is also new and they don't build up a knowledge of how to use the equipment either. Okay. Well, Luca already explained in some detail why we would want to use planning for human-robot interactions, but specific to our domain, I suppose, it's about this correctness of the solution and the less effort for the design of the system. So this kind of interaction we're building is like a conversation between the robot and the user, and everything that the robot is going to say, all of the information it has to impart or questions it wants to ask, these are already prescribed. Someone has to have written this kind of content, and what we want to use the planning to do is to link it together in a way that makes sense, that is more like a conversation than just a huge column of data. And this is something a user can do by constructing the conversation, but it's quite arduous, especially if the interaction includes many different things that could be said. And maybe you manage to put together a lovely dialogue system as soon as someone comes with new constraints to say, okay, your survey robot on the ICAPS floor, I want to make sure that after it's asked all its questions, it at some point in the conversation has told them where to find the conference banquet. You then have to, okay, well, let's add that information into the dialogue tree and make sure that it's 100% guaranteed that that information is going to be imparted, and also it doesn't look as though it's just being tacked on at the end, but it's a natural part of the interaction. This is something you can do simply by changing the goals in a conditional planning problem. So for us, planners was sort of the natural thing to use to put this content together. So we're using conditional plans which generate either DAGs or trees like this, which you can see is a really kind of nice analog for the kind of dialogue trees that non-planning people have been writing for video games and similar things many times. So this is what we want our plans to look like. We want them to be like a dialogue tree. So we used ROSPlan on the left-hand side to just pass our domain and problem files and create these dialogue trees, here the plan pie, and then pass them onto the PNP library for then to be executed on the robot. I'll quickly go into a kind of introduction to what the Petri Net Plans are. So this is the way in which we want to represent our plans. Petri nets are consisting of kind of places and transitions, and you can put little tokens onto those places. And then they behave by, whenever these transitions become true, you take the token off the preceding place and you move it onto any of the next places. And this is how they evolve. A Petri Net plan, in particular, is a kind of subcategory of our Petri nets, which are Petri nets formed of actions, which are kind of little subtree things, and connected together with operators. So, for example, an ordinary action consists of a place for the action's not started yet, the transition for when it's supposed to be executed, the action's currently executing, then the action finishes and you're in the sort of post-action place. And then a sensing action would be a similar thing, but the execution would branch depending on whatever conditional effects there are of that action. So you can see a Petri Net plan then would be combining these things into a much larger structure. The Petri Net also allows us to use interrupts. So this is something we can't really define in the PDDL domain, where if a certain condition becomes true while we're executing an action, we want to interrupt that action and react to this event. So the go-to ball currently executing, if the ball was stolen, would interrupt the normal execution of the plan and go somewhere else. I'll explain why this is useful in a little bit. So here's an example of what a Petri Net plan might look like, where there are sensing actions, there are loops, and it's all of these actions combined together. The takeaway message here, though, is that the Petri Net plan is exponentially more expressive than something like, say, transition graphs. So we can easily describe our dialogue systems and a little bit more. Right, so just expanding what that PNP box looked like before. We're creating this plan and passing it to this robustification step, which I'll describe in a second, to represent this dialogue tree plan as a Petri net and then executing on a robot. If you ignore that execution rules arrow in the robustification step, that Petri Net plan is just describing the conversation tree that was generated by the planner, and it's to be executed as it looks. One thing to note, that everything inside this blue box is meant to be domain dependent. It doesn't matter what your service robot's doing. You can download this kind of software library and run it without having to change anything. And this is online now. There are links at the end. And more than that, everything outside the blue box is not written in C++. It's sort of a declarative input into the system, and I'll go into that in a bit more detail after I explain what I meant by the domain being a domain-independent thing. So I mean that there is kind of two levels of what is domain-independent here. The planning domain is in the domain of service robots. It's creating a dialogue tree, but that's independent from the context of the kind of conversation they're having. Right? So the domain is written very abstractly, and there are tokens that the robot can give to the user. There are questions that can ask, and these tokens can be combined or follow one another in various different ways. But the context of the interaction is separate from that. That would be described in the problem instance, which is input to the system. So when you combine this context of the interaction with the domain-independent domain, then you can generate this kind of dialogue tree. But the context can be defined by a non-PDDL person. All you need is a tool to be able to pre-write all of those interaction content and questions that I described earlier, and in some way phrase how they can be linked. And then the problem instance can be generated automatically. All right. So here I'll come back to now, what do I mean by this? Everything outside of the box is not C++, and what are these execution rules? So this conversation tree that's been generated, that describes the nominal behavior of the robot, right? That's the execution trace that we expect to happen if the user behaves and acts exactly as they were modeled. But this is never going to happen. I mean, as Manuela was talking about this morning, you have a robot like sitting in the office waiting to guide someone, but that person's just not there. Or they've gone to get the coffee, but there's no one to make the coffee for them. And in this case, I guess you can send an email to ask for help. That's one kind of recovery procedure. And you can define all kinds of recovery procedures. And usually what I would do is I would hand code the recovery procedure, maybe into the execution of the actions or into the execution architecture that's dispatching the plan. I would say, okay, well, if this, then do this. But we want to be able to perform these recovery procedures, or at least describe them, without hand coding them in C++. So that's what these execution rules are, and this robustification step. The execution rules allow you to add these conditional statements to the plan to allow for recovery paths, or to make sure that the robot adheres to certain social norms, for example. There we go. So here's some examples. So you could say that if the robot was moving towards a target to greet a person, but that person was standing in their robot's goal position, you don't want the robot to try and kind of shuffle around until the person moves out of the way, finally move into the goal position, turn around and say, hello, I'm here. You want it to stop as soon as it sees the person and say, oh, hello, you're already here. So this first execution rule here is saying if the person's here and we're already close to target doing the go-to action, then just skip the rest of that action. You can stop and you can say hello. And you could define a recovery procedure to send an email here, or even to say, well, if certain conditions are met, then cancel the plan and replan. So when you combine these conditional statements into the conditional plan, the Petri Net can describe it still, and it becomes a much more sort of complex looking structure. But this can be executed. And our conversation trees start to look something more like this. All right. So to conclude, we developed this system using conditional planning and a Petri Net plan execution to perform short-term human-robot interactions on service robots. And what we were concentrating on is a separation from the planning that's performed and the actual system on the robot and the context of the interactions which a non-expert user would be able to write. And this is then combined with the execution rules, which are also declared in a declarative way to provide kind of robust execution. You can get all of the source code online from the PNP library and ROSPlan. And thank you. That's all I have.
Questions? Yeah, one.
So can you talk a bit about what kind of knowledge or information goes into your system before it does its conditioning? What are the inputs?
Okay. So in particular, the problem instance is the main input, I would say. The execution rules are the second part, but maybe they stay the same, or some of them will stay the same. The problem instance in this case has to include all of the content that the robot is going to say. So it would be either questions and the possible answers, and also the kind of blocks of text and images that the robot might be able to show. And these are encapsulated in what we call tokens. And then there are some facts which link these. So you can say that in the initial state, most tokens aren't available just to be given to the user. They have to be activated first by either the user asking for them or the robot learning that this user has some certain properties that activates the token, and then they can pass it over.
Other questions? Yes.
Can you describe a bit how the execution rules take place? So you're saying that you're not hand coding the recoveries, but how much information needs to go into these execution rules that's going to be guiding these recovery procedures? So isn't there a lot of sort of hand coding that you would need to put in for that piece? I'm not sort of seeing that part of it, I guess, if that makes sense.
Yeah, so I should have said this is where the interrupt kind of function of the PNP becomes really useful. Because
you need a lot of domain knowledge to be the person that's writing the execution rules?
Yeah, I think that's the case. You would need to know at least somehow how the various predicates of the domain are formed in order to be able to write these execution rules.
So where's the advantage that you were saying where you're not hard coding the recovery strategies?
There's sort of two main advantages. The first is it's very quick to write these recovery procedures, and it's very easy to change them. Whereas sometimes things can get lost in the C++ code, and it's a bit more difficult to change.
But if there's a situation that arises that you don't have in your execution rule, like what would happen? Does the robot know how to recover in that case?
So if you don't have an execution rule for example, you don't have anything for the person's not here and you've said hello and you're still waiting for a response. If you have no execution rule for that, then the robot will just wait. Similarly, if you haven't hand-coded a recovery procedure, the robot would just wait.
You could easily have a catch-all procedure, right? Timeout or something. It's easy to get out of.
Yeah.
Okay, other questions?
Can I ask one more?
Yeah, sure.
So, in terms of the, I understand the execution rules. Can you go to that, remember the block diagram kind of thing you had?
Yeah, this.
Yeah, this one, yes. So again, going back to my question, the context, you define that, right? Or
yeah, the
context.
Yeah. So this would be the PDDL instance, right? The problem file.
But if I did not want to do PDDL, I could still do other things, right? If I wanted to, it should not matter.
Right now, you have to put it into a PDDL file.
Okay. No, you can generate.
But what we're planning next is for just like a nice user interface where you can type in without any knowledge of the PDDL problem, the syntax, and generate, and it'll create the file.
It's actually giving you a chance to emphasize things. In the sort of interaction context, if PDDL is required now, if instead I use some other system and gave you something that your ROSPlan could use, you wouldn't care, right?
Oh, well, that's true. Yeah.
That's what I was trying to ask. Yes, yeah. I was trying to understand which parts are independent and which parts are bound to a specific formalism. It looks like this is not, though you're using PDDL in a system requires it, that's not essential. I could do something else as long as the plan comes into the ROSPlan. Is that right?
Yeah. Well, in fact, as long as the plan is in a format that the PNP can recognize as input,
yes,
you could also replace sort of everything on the left. Yeah.
Okay, all right. Let's thank the speaker again.